Now, when we are studying about the metamorphism of H2O or CO2 induced or reactions which have H2O or CO2, those are generated. They actually, what they sort of do is that being produced in the system, they change the entropy of any substances or increment of entropy. Now, the changes of the entropy, as we know, they can actually control the Gibbs free energy of the equations because G is equal to H minus of T to the beta. And because of these changes of the large entropy in a devolatilization reaction, the metamorphism of there are some changes during the metamorphic process, or they can substantially control the pressure temperature range of a metamorphism which we can actually observe in a system. Yes, these factors. Now, the fluid phase in most metamorphic rocks is dominated by H2 and CO2, and both of these initially derived almost entirely from the atmosphere or meteoric, that is we call the meteoric water or meteoric substances, and as well as the clays and the other water bearing minerals like micas can also show you or can also contribute to this to these H2 and CO2 in a system. They can be tracked directly in the pores of the fluid, but during compaction and diagenesis of sediment, most of these get expelled from the system. The fluid phase in metamorphic rocks is therefore derived largely from the breakdown of minerals rather than from the initially trapped pore fluid. The pressure, volume, temperature of the fluids and the reactions, which we can find the equation of state as V is equal to B plus RT by K, and this equation is well known as van der Waals equation. V is equal to A plus RT by P, or B. That is, an obvious flaw in the ideal gas law is the prediction that the volume of the gas decreases to zero at the absolute zero of temperature, but the gases must have a finite volume at absolute zero, and most of course liquefy well above this, and then their volume changes very little with falling temperature. And the ideal gas law can be modified by assigning to the value B in the finite volume which would exist at the absolute zero, because and this equation, or rather if we can adjust this equation of the ideal gas law, the pressure that causes the gas to expand must be diminished by an attractive force between the molecules. That is, whenever the molecules are in attraction, there won't be a change of the volume, and which is known as the van der Waals force, and the pressure must therefore be reduced by this amount. To do this, we first rearrange this equation to P is equal to RT by V minus of B, rearranging this equation. And now there is a problem, and we can actually, the pressure must therefore be produced. To do this, rearrange this equation from this we subtract the amount A by del V square, where A is a constant and del V square is the amount that is introduced to account for the fact that the attractive forces in between the gaseous molecules, the attraction between the gaseous molecules, and produce an imbalance only on the outer walls of the volume. That is, in the volume, the outer balance में जो है, the volume में, they will be try to adjust themselves, and they will try to rectify the volume with respect to, and their terminology we are getting is that V square. Now these equations can also be modified from van der Waals equation to much more modified equations, like where we can substitute the a by v del v squared term by root over t v bar plus v bar plus b. And under more extreme conditions, these are encountered in case of metamorphism, and van der Waals equation is being modified by root t into v minus of b. This can be rearranged, and these are actually found by the experiments we have done in the fields of metamorphism. And the ideal gas fluid high temperatures where the volumes are large, because the second term on the right hand side y approaches to 0 and y approaches 0. And there are some problems in this, there might not be some problems in this. The fugacities, once equations of states are known, the integral of VdP in equation H4 can be evaluated and the free energy change of the reaction involving a gas under any desired condition can be determined. Recalling this equation, it will be recalled that equation 87, that a function known as the fugacity was introduced so that the simple form of the integral volume V bar dP for ideal gases could be retained for non-ideal ones. That is, the integral is RT logarithm of F. By equating the actual integral of V bar dP obtained using the equation of state RT logarithm of F. Repeating, that once the del V dP term in the equation can be evaluated by the free energy change of the reaction involving a gas and any desired condition can be determined if the equation of the state of the ideal gas RT by P is substantiated by RT into logarithm of P, that is, we are converting or we are changing the P value, or we are rearranging the P value in terms of logarithm of pressure scale, then the term can also be changed. And as we can see that VdP, that is change of pressure with respect to the activity, that will be controlling another factor which is called as fugacity. Fugacity is a function of pressure. Okay, it is a function. Now, whenever we are trying to accept the fact that the Gibbs free energy, that T is a function of H, T Ds, V, dP, and mu I given I, the dP term can be reduced by this fugacity term as well with respect to the activity term. Now, the mineralogical reactions which can substantially be changing the atmosphere, or rather the conditions in which the metamorphism is taking place, and the dehydration and decarbonation reactions in the presence of a mixed fluid phase involve three intensive variables, that is pressure, temperature, and fluid composition, because X is there, P change is there, fugacity change is there, as well as temperature is there. A decarbonation reaction or a dehydration reaction, to determine the conditions under which a decarbonation or a dehydration reaction will take place, the shape of the reaction surface in terms of pressure, temperature, fugacity of fugacity of carbon dioxide, or the concentration of carbon dioxide and the concentration of the H2 in the system must be analyzed. Because in the previous session we have seen that the presence of a fluid in a system, that is, which can control the activity because of the presence of the fluid of Xi molecule, and suppose the fluid, because we have seen in case of the dioxide and anorthite in the system, that can change the activity of the dioxide and anorthite in the component. So, as we can observe, that can be the cause of change of the melting point in a system. the reaction into these input component parts and then expresses the function of pressure, temperature, fluid composition. We generate the equation needed to describe the reaction surface. Although the derivation may appear complex because of the number of terms involved, because you can see that because of the presence of the mineral phase, because of the presence of separate mineral phases, because of their contact regions, because of the presence of carbon dioxide, because of the presence of H2O, because of the presence of pressure, volume, as well as there is another thing which we don't encounter, which we don't consider in metamorphism, that is the Helmholtz free energy, that actually signifies the differential stress along different directions. So the number of variables you can imagine, just only if the chemical potential of a reaction might have 10 or 12 variables, how much of variables could be there? 20, 25 or much more than that. And this is classically, it is type of boundary kind of value problem in case of a metamorphism, where we will have to analyze the system or the components of the system from different perspectives to know how much to give where. I mean, कहाँ पे कितना देना है, कहाँ पे कौन सा वाला बाउंड्री वैल्यू लेना है, कहाँ पे 1000 डिग्री सेल्सियस देना है, कहाँ पे एक्टिविटी आयरन टाइप का 0.5 रखना है, कहाँ पे 0.49 रखना है, वो सभी आपको डिटरमाइन करना पड़ेगा. और उसी वजह से highly these types of diagrams we use nowadays the softwares like Partplay, softwares like Thermocalc, etc. to somehow do it much more earlier, much more faster, as well as it will release the pressure, because the iterative processes, the iterative functions are must best done by machines. And now for this reaction, if the reaction is like A is equal to B plus mole of H2O plus some mole of CO2. A is just left hand side of the reaction, B is just the right hand side of the reaction, just for the. And now we can see that there will be also a turn of this range of G's, this, and there will be a mixing turn, that is if fluid is mixed in between the components or among the components of H2 and CO2, that will indeed add up some other terminology in this aspect. Now, the energies of the various phases, a free energy term resulting from the mixing of the fluid components is included, that is del G of mix, and if the reactants and the products are in equilibrium on the reaction surface at a point represented by T0, P0, X0H and X0C, how will the del G change with respect to pressure, temperature and composition? In section 1.6, the temperature at any depth in Earth was determined by expanding T and the Taylor series as a function of depth, starting from the known temperature on the Earth's surface, and similarly del GT can be expanded as a Taylor series as a function of pressure, temperature, composition. Only the two first term series need to be used for the expansion, because eventually the expression is used to determine the conditions at a point that is separated from the first place or the first point by dp, dt and dx. Now, for any given situation or any instance, we can say that if we are trying to consider the temperature at a given point, that is gives free energy Tp. Notice that only the phase B is taken in this equation. It will be Gb, that is the standard, plus or minus plus del Gb by T at constant pressure and composition into T minus of T0 plus del Gb by del P temperature composition at P minus of P0, because T0, P0 they are taken in the surface of the Earth, and T and P are the conditions at which we want to do that. In case of the first component, which was GATP, will be like reiterating the form of the equation, they will be the same. As well as for the free energy of the fluid is a function of temperature, pressure and fluid composition, and also at constant temperature and pressure the free energy of the fluid is given by, that is chemical potential of M, that is water into the molecules of the water, plus N into chemical potential of C, that is the chemical potential of the carbon dioxide in that situation. Okay, and this whole idea of this equation from the book of Philpotts at page 498 will give you a situation where the chemical potentials of the components of water and carbon dioxide are taken, as well as the changes of pressure and the temperature are taken, and they will be minimized in the form of M into chemical potential of change by T pressure XH C minus of XH plus MR logarithm of XH. The partial derivative with respect to pressure can be expanded as from other reaction in another form of the reaction. Now, these two things will not be invoked from these three things, or rather we will have to find out that how the CO2 or the H2 or their partial pressure can actually contribute to the changes in the mineralogical transformation or the generation of the water on the right hand side of the reaction, any reaction. Now, standardizing, or rather from these equations we will be finding out that number of the carbon dioxide or the number of the moles of the carbon dioxide as well as the number of moles of the water will be playing a significant role in the final Gibbs free energy, or the determination or the resultant of the resultant Gibbs free energy which we can find in the system, from which we can say which way the reaction should go. And they will also generate some curves in the pressure temperature phase or the pressure temperature space, or the pressure and carbon dioxide concentration space, as the components as well as the system components will not, or the resultant of the component Gibbs free resultant of these processes will not be linear at all. They will be curvilinear in fashion. Just as an example, see the figure 27 from the page 499 of Philpotts. Now, where does these fluids or which have been generated due to these reactions go? Now, as we know that the mechanical dispersion, advection and diffusion are not only the ways to transport the material into fluids. Another process called the mechanical dispersion can be very important as well. Imagine that a drop of dye is introduced into the fluid moving through a porous rock. In the page 518, the dye will disperse because the flow path mix due to the tortuosity, and because of the fluid velocities in adjacent pores differ somewhat due to the small differences in pore geometries. As a result, the dye spreads out both in the direction of the flow as well as the transverse to it. The degrees of the spreading of the increase with distances from the point. And although the mechanical dispersion is the result of the advection, its effects are like those of diffusion. Therefore, the process is treated mathematically like the diffusion. Therefore, the process is treated, and in order to do this, coefficients of mechanical dispersion analogous to diffusion coefficients are defined. That is, dmdl is equal to alpha L into Vx. dmdl that is considering the flow of the transport of these masses in one dimension, where alpha L is the coefficient of dispersivity in the direction of the flow, that is longitudinal dispersivity, and dmdl is the corresponding coefficient of mechanical dispersion, and Vx is the absolute value of the pore velocity. Now pore velocity, which means the velocity of these components which were being reproduced from the reaction, that is carbon dioxide H2. So if in a metamorphic terrain, suppose there is a metamorphism is taking place, and in presence of the CO2 and H2, and they are creating these paths, and as well as they are getting dispersed through this, and there will be very few parameters we will be knowing. Most of the parameters we will not be knowing, as well as there are problems in the buffer, in the geology, in the metamorphism, that how much or what type of a fluid or what type of a buffer was present in the time of the metamorphism when these processes were acting on. Now, coming back to the study of the tourmaline for Anil and Trija, what we have seen in the veins of this area is that we are finding a good amount of quartz, and there is absolutely no feldspar present, as at least as observed in the microscope. There might be very little amount of feldspar which are crystallized in the field, and those quartz veins are shows a good amount of tourmaline, which again shows zoning. Now the question is that if SiO2 is present, there must be some supersaturated fluid in SiO2. We don't know the PCO2 or PH2 in that situation. We don't know where the third generation or the second generation of the tourmaline is coming from, because they have taken very little amount of shear deformation around, as well as we have least idea whether there was a previous mineral which were being transformed into the third generation or the second generation of the tourmaline. But by far, the only thing we know is that the first generation of tourmaline is pretty robust, and so whenever we will be trying to give it out or give these informations out in front of the audience, try to be very much specific regarding these informations, as well as you can now understand how complex these things can be, as it can be problematic in itself in case of the tourmaline, because tourmaline is itself can be different types of elements, and there is no one EPNA analysis can do nothing. There must be a Zahn spectrometry, there must be a SIMS to know the trace element amount, there must be a Zahn spectrometry to know the ferric and ferrous amount, so we can do it or make the calculations more perfect manner. And we still don't know. However, we know is that there was a shear zone which was affected by fluid flow, and then there was a tourmaline formed. It was probably in a low grade of metamorphism. As we can see the mineralogical assemblage. There was a thrust contact, and there are some very good type of recumbent folded structures which have been preserved all over the area. So so later much we will be analyzing those tourmalines and the adjacent rocks when the money of funding is right. Then we will be much more akin to understand and analyze what situations were taking them to form or to grow. But however, it is not a deep mantle condition, as we can see, and there is no very high pressure mineral which was formed. So obviously, I think the equation of state will be pretty close to the known ones.